All right, so today we're diving into a paper that doesn't just tweak how AI creates images, it completely challenges one of the core ideas behind it. We're talking about a new philosophy that leads to higher quality images and dramatically faster training. So let's break down how they pulled it off.
I mean, we've all been watching this space. Generative AI has gone from creating these blurry, weird shapes to stunning, photorealistic masterpieces. You know the drill. You type in a corgi riding a unicycle on the moon, and boom, seconds later, there it is. It really does feel like magic, doesn't it? Like some black box just understands.
But what if I told you that the standard method, the very foundation that most of these incredible models are built on, is actually kind of inefficient? That we've been accidentally forcing our AIs to work with one hand tied behind their backs this whole time?
Yeah, the whole issue really comes down to what I'm calling the AI's blueprint problem. And it all starts with how an AI first gets its head around the image it's supposed to create.
You see, before an AI can generate anything, it has to create this compressed internal map of an image. In the biz, it's called the latent space, but honestly, just think of it as a blueprint. And just like in construction, the quality and the detail of that blueprint, well, it determines everything about the final picture.
Okay, so this is where it gets really interesting. The old method, which uses something called a VAE, is all about aggressive compression. It's like taking a beautiful, detailed architectural drawing and then crunching it down into a blurry little thumbnail just to save some space. You lose so much vital information. The new idea, using a representation autoencoder, or RAE, basically says, hold on, forget that. Instead of squishing everything, let's use a really powerful, pre-trained AI to create a rich, detailed blueprint right from the start.
And here's the kicker, the part that's just wild. Not only is the old VAE blueprint lower quality, it's also way more expensive to make. This table shows the computational cost. Just think of it as pure processing power. The new RAE encoder is 6 times cheaper to run. The decoder, 3 times cheaper. We were literally paying a premium for a worse product. Crazy, right?
So, this brings us right to the heart of this research, the whole idea of building a smarter blueprint by just challenging the old way of thinking.
And the researchers, they don't mince words. They put it right there in the paper. For years, the field has been operating on a couple of big assumptions about how to create these blueprints, and, as they say right here, both assumptions might be wrong.
So, what were these two big myths? Well, first, everyone kind of thought that AIs that were good at understanding the meaning of an image, what's actually in it, couldn't possibly be good at reconstructing all the tiny pixel-perfect details. And second, the conventional wisdom was that the AI builder, the diffusion model, just couldn't handle the super complex, detailed blueprints these smarter AIs would make.
And oh boy, did the data prove those myths wrong. The RAE blueprint is just flat out better at reconstruction. That RFID score is lower, and that's good. But just look at the semantic understanding. This is about whether the AI actually knows what it's looking at. The old VAE, it's right about 8% of the time. The RAE, nearly 85%. That is a monumental, jaw-dropping leap in comprehension.
Okay, so the researchers created this vastly superior blueprint. Awesome. Problem solved, right? Well, not quite. Turns out the AI builder, the diffusion model, had only ever seen the old, simple, blurry blueprints. It had no idea how to read this new, complex, beautiful design. So that became the next big question. How do you teach an old dog new tricks? I mean, how do you upgrade your builder so it can handle a blueprint that is just orders of magnitude more complex than anything it's ever seen before?
Well, they came up with 3 really clever fixes. First, to handle that richer blueprint, they essentially gave the builder a wider foundation to work on. Makes sense. Second, they changed up the training process to account for all that dense new information. And third, and this is super smart, they actually taught the final part of the process, the decoder, to be a little more forgiving, to basically anticipate that the builder might make a few tiny mistakes when working with such a detailed plan.
And this is the payoff. By starting with a better blueprint and then teaching the AI how to use it, they didn't just get better images, they got them in a fraction of the time. To reach the same level of quality, the standard old method takes 47 times longer to train. 47! That is not a small improvement. That is a fundamental, game-changing shift in efficiency.
But they didn't stop there. After completely revolutionizing the blueprint and retraining the builder, they decided, you know what? Let's give the builder itself a massive upgrade. So if the diffusion model is our builder, they decided it needed a new, way more efficient foreman to manage the whole construction process. And this new foreman is an architectural trick called DITDH. Now, DITDH is a bit of a mouthful, I know, but the concept is actually really elegant. They took a standard diffusion transformer and just tacked on this special module at the end, a head that's very shallow but incredibly wide. This gives the model all the performance benefits of having a huge, wide architecture, but without the massive computational cost. It's truly the best of both worlds.
So now we've got the whole package. A superior blueprint with RAE, a builder that's been trained to read it, and a supercharged foreman called DDH. So what happens when you put all that together? You don't just get better results. You break records.
1.13. That is the new record FID score on the gold standard ImageNet benchmark. Now remember, FID measures image quality, and lower is better. For a long time, the best models have been fighting tooth and nail over tiny fractions of a point. This sets a completely new standard.
And just to put that number in perspective, take a look at this. It doesn't just squeak by the previous records. It solidly beats all the previous state-of-the-art models. This isn't just another step forward. This is a serious leap.
The researchers themselves make a pretty bold claim in their conclusion. They state that this RAE approach has such clear advantages that it should be the new default for diffusion transformer training. They're not just showing off a cool new model. They're arguing for a whole new foundation for the entire field.
So let's just sum it all up. Why does this matter? Well, first, it's a whole new philosophy. Stop aggressively compressing and start richly representing. The result? It's an approach that is both faster and better, and it's establishing a new foundation that we're probably going to see powering all kinds of creative AI tools very soon.
Which of course leaves us with one final really exciting question. What will artists and creators and all of us build now that AI generation is getting this good and this fast? What kind of new tools, what new art forms, what new realities are going to be built on top of this incredibly powerful new foundation? I would love to hear what you think in the comments below.